who actually allows them to film the entire construction process from the rooftop. So let's enjoy.
Between 2015 and 2019, a unique public building was built in the city of Kuching, in the state of Sarawak in Malaysia. This time-lapse video shows the construction of the iconic Sarawak Museum complex. In 2014, under the experienced management of PPES Works Sarawak, the design and build contractor, the project received green light from the state government. Kuching-based architect AKDI signed for the design of the 30,000 square meter complex. A spacious and functional museum was designed through peer review sessions and international guidance from museum colleagues in Asia and Europe. It is built according to the latest sustainability guidelines from the Malaysia Green Building Index and is the first certified GBI museum in Malaysia. Designed with all modern public facilities, it houses large collection storage facilities to keep the important museum collections safely preserved for future generations. Dedicated research laboratories support the museum's ambition towards becoming a research institute. As a center of learning, the new museum welcomes international scholars to research and document the material knowledge of Borneo's rich past, its cultures, its people, and its nature. The museum will be reaching out to a broad audience, young and old, scholarly or just curious, to both residents and international visitors. By end 2020, the world-class museum will open its doors to the public with a new 6,000 square meters engaging exhibition. A well-curated selection of unique artifacts and specimens will be telling multiple stories about the history and life of the people of Sarawak. The Sarawak Museum Complex is just the beginning of a new era in preserving and displaying Sarawak's rich heritage. You might say the building holds together all those precious museum objects as a rattan woven basket holds its content. We hope to see you soon and to be able to welcome you in Kuching in the iconic Sarawak Museum Complex.
Alright, so I will first start off my presentation with a brief introduction of the project's background. So this new Sarawak Museum Complex is actually a project of the client of this project is Jabatan Museum Sarawak in collaboration with our JKR Sarawak. And the main contractor of this project is PPES Works Sarawak Sdn Bhd, whereas for the design architect for this project is it's actually designed by architect KDI. And the CNS engineer for this project is EDS Consultants Sdn Bhd, whereas for the quantity surveyors for these projects are JUPSA Sdn Bhd as well as PUBM Quantity Surveyor Sdn Bhd. So this museum is set to be the largest museum in Malaysia, and it is going to be the second largest museum in Asia also. So we, ANNEX Bluescope Lysaght Sarawak, is actually the roof contractor, which is awarded under the package 4 in these projects. So our scope of work includes the supply and install for the roof truss and the roof coverings for the annex building and the main building. Next, let's have a look at these photos. This is a photo showing the overview of the entire project. So as you can see here, I will go through a brief introduction of each individual buildings. Okay, so the biggest building that is right in the middle of this photo is actually what we call the main buildings. So this main building is actually a 5 stories buildings with a combined total roof height of around 43 meters. So the building that is next to the main building, which we call the annex building, this annex building is actually a 3-story building, which is right at the back of the main building. And over the right hand side of the main building over here, we have got a pedestrian bridge in which we call the green connector. So this green connector is actually a pedestrian link bridge that links the existing museum. Existing old museum is over here to the main building of the new Sarawak Museum Complex over here. So we have also got arrival canopy at this side, as well as the covered linkway, which actually links the existing Islamic museum over here to the new Sarawak Museum. So today I will mainly share with you. I will focus mainly on these two buildings which actually under our package, which is our main buildings as well as the annex building. So we will first start off with the less complicated one, the annex building first. Okay, so this is a close-up photo of the annex building. So this annex building is actually a building that is connected to the main building via a platform over here, which at level 2, which we call the level 2 platform. And these annex buildings actually consist of 3 roofs. As you can see here, the lowest level roof over here is what we call the level 2 roof. This level 2 roof is actually a single pitch roof, and it is a pretty short roof. And the roof pitch is at 3 degrees. And we have got another roof at the back of the building over here, which is the level 3 roofs. This level 3 roof is also a single pitch roof with a roof pitch of 3 degrees as well, but the length of the roof is much longer than that of the level 2 roof. This roof is around 14 meters. And lastly, we have got this level 4 roofs, which is actually the biggest roof of the biggest portion of the roof is actually contributed by this portion of the annex buildings. This roof is in contrary to the other two, this is a hip roof, but this hip roof, instead of falling in 4 directions, it actually falls in 3 directions with a parapet wall at one of the sides. And the roof pitch for this annex building roof is slightly higher than that of the 2 other roofs, which is at 5 degrees. Okay, next, I would like to share a bit with you on the roof specifications of the annex building itself. So we'll start with the roof truss first. If you know that roof truss is actually the components that actually supports the claddings. It serves as a structural components that supports the cladding from flying off, as well as to sustain additional weight that when people do maintenance on top of it, it has to be made sure that all these trusses do have enough capacity to support the required weight. So for this annex building, we are actually specifying our Lysaght proprietary smart truss system in 2 core components. And this smart truss system is actually a lightweight cold form steel truss system. And the good thing about this smart truss is that it has all the components in the trusses are actually having a very high strength to weight ratio. And secondly, it is also termite resistant because it is steel compared to timber. It is subject to termite attack. And for this, when it comes to steel, you won't have this problem. And of course, like what I mentioned just now, this is a lightweight roof truss, lightweight cold form roof truss, and the thickness of the components are actually very thin. So it is relatively lightweight as compared to conventional mild steel structures. When we talk about lightweight structures, it means that it will contribute to lower foundation costs. And last but not least, our smart truss system is also designed and detailed by our in-house software, which we call the SupraCAD. And this SupraCAD is actually developed by our Lysaght Technologies R&D in Australia. And this Lysaght R&D in Australia is actually a accredited lab in Australia, where it has gotten the accreditation from the NATA, the National Association of Testing Authorities Australia. So all the accredited labs needs to be endorsed by NATA before in order to have all your data validated. So all our design data in our SupraCAD is actually validated by NATA. And ANNEX Bluescope Lysaght is also an approved conform steel truss system provider by JKR. If you go to the JKR website or the JKR conform steel truss system provider list, you will see our name in there. And of course, in this project, as this project is a JKR project, it is under the supervision of JKR. So all of our truss design needs to be designed in accordance with JKR specifications for prefabricated cold form steel truss. And the components of these trusses, the specifications of the components of these trusses is G550 AZ150. So this G550 is actually the tensile strength of the components of the trusses. So G550 means that it has got a tensile strength of 550 megapascal. Whereas for this AZ150, this AZ150 is actually the coating mass of the components of the truss. So AZ150 means that it has got a zinc-aluminum content coating of 150 gram per meter square. So this value, the higher the better. It means that when you have got a higher value, it means that it is more durable. And next, for the truss members, such as the top course, bottom course, and webs, we use a minimum. All our members actually have a minimum thickness of 1 mm in this project, because in accordance with JKR specs, all your truss components, not including the patterns, the truss components itself needs to use a material of thickness of minimum of 1.0 mm thick at least. And of course, the JKR specifications also requires that the truss spacing has to be spaced at maximum 1.2 meters centers to centers, not more than that. Okay, so I would like to share with you a little bit on the construction of our how is our truss constructed. So I will take the case of level 4 annex building as an example. So as you can see, these are the truss that has been installed for the level at the level 4 for the annex buildings over here. And all the fabrication of the trusses, the assembly of the components of the trusses are actually done at level 2 platform over here. The one that I've shown you just now, the platform that connects the main buildings to the annex building just now, this is where we are doing our fabrication of our trusses. So for this one, if you look at this is a very wide building. You see the grid over here. This grid is already around 8 point something meters. So each grid is actually on the average of around 8 meters. So by proportion, if you look at this, the actual width of the buildings including the overhang is actually 42 meters. So imagine if you are to fabricate a truss of this long on the ground over here and lift it up and to be installed at the level 4 rooftop, is going to be a very hectic job, and it's going to incur a lot of time and labor costs in this. So what we are doing in this case is that instead of fabricating the full single truss as a continuous components, we are actually fabricating each and every truss as a simply supported. So we actually divide this truss into 5 separate simply supported trusses. So by doing this, we can save a lot of time as well as the labor cost when it comes to the installation. It will be much easier, and it requires less worker, and there will be less safety concern when it comes to the installation and the erection of the trusses. Okay, that is about the trusses. Next, I will share with you on the roof specifications for the insulation, the specifications of the insulation of the annex buildings. So for the insulation, for the scintillation, we are actually using our Lysaght Thermacool bubble as our radiant barrier. So our Lysaght Thermacool bubble is an 8 mm thick bubble foil with 20 mm bubble laminated by aluminum foil at both sides. So as you can see from this diagram over here, this is the build-up of our Thermacool bubble. You can see that there is a 20 mm size bubble in the middle of the foil, and is laminated by pure aluminum at the top and at the bottom. And of course, this is also a self-supporting aluminum bubble foil, because we have got a woven fabric over here, which actually provides strength to support the rock wool. So in this case, we are no longer using any chicken wire mesh to support the rock wool over here, because this aluminum foil itself is capable of sustaining the weight of the rock wool itself already. And of course, our Lysaght Thermacool bubble is also Bomba Class O certified as well, and it is also registered under CIDB certified construction materials as well. As for the blanket insulation, we are actually using 2 layers of 50 mm thick, 40 kg per meter cube rock wool as our thermal and acoustic insulation. So this is how the rock wool looks like. Okay, now we have gone through the truss, the insulation, and the last one would be the top skin. The top skin of the top skin of the annex building, we actually specified our Lysaght Clip Lock Optima profile. The profile that we are specifying is actually our Lysaght Clip Optima profile. This Clip Lock Optima is actually our concealed fixed profile with proprietary KL98 tower clip system. So since this is a concealed fixed profiles, so it is unlike those pierced fasten profile where you can see the exposed fastener on top of the roofs. This is it will simply means that there's less chances of water ingress when the fasteners fail. And we have for the Clip Lock Optima, for this Clip Lock Optima profile, it has got a rib height of 43 mm, tall rib heights, and cover width of 980 mm. So you can see that this is a very wide pan and high ribs profiles. So that is why it can goes down to a minimum roof pitch of 2 degrees. Our case for the annex building is actually 3 degrees for the short roof and 5 degrees for the longer roof. And you can see that it is actually there's no problem at all using Clip Lock Optima because it can go to a minimum pitch of 2 degrees or 3.5% slope. This is on the profile. And next, on the material itself, what materials are we actually using or specifying for this project? So the material that we are proposing for this project is 0.48 mm BMT, 0.53 mm TCT, Colorbond XPD pearlescent steel. So this XPD pearlescent steel series is actually a very special series, which is specifically developed for applications that demand the ultimate performance in both long-lasting colors and gloss retention. So this is a very special product series where it is kind of like a metallic version of the Colorbond. And also it has also got a custom formulated 70% PVDF paint system with high performance mica pigments. And the name of the colors of the that we are actually giving to this color, to the color that we use for the Sarawak Museum, is actually pearl gold. So for those of you who happens to actually browse through our XPD pearlescent product brochure, you won't be able to find this name, this color inside the brochure, because this color is specific. It is actually tailor made to match the color of our existing state assembly building in Sarawak, which are our Dun buildings lah. So in fact, we have also visited the Dun Sarawak building several times to actually to get a piece of the small sample to actually, in order to make sure that the colors that that we actually use for the Sarawak Museum actually match the colors of the Dun Sarawak as close as possible. Okay, so I will show you an overview of the roof build-up. But first, before that, I would like to share with you on this. So as you can see here, this is a conventional single skin roof build-up. This is how a single skin roof looks like conventionally. So normally when you do a single skin roof, what you are doing is that you are going to put on a single layer of this aluminum foil scissellation, after which you put on your rock wool. And after you put on your rock wool, then you can straight away put on your top skin already. In this case, it's Clip Lock Optima. So you can see that we can actually, if it is a 50 mm 40 kg per meter cube rock wool, you can easily just compress it. And after you lay the batten, you can straight away put on your foil, put on your rock wool, and put on your top skin. But in our case, it is not that simple. It is slightly different. Even though annex building is also a single skin roof, you can see that it is only a clip. It is also Clip Optima single skin, but it is slightly different in a way that the insulation that is actually used is actually, instead of 50 mm single layer, we are actually using 2 layers of 50 mm thick rock wool. So that is the reason why we cannot do it this way, like this conventional way, because we won't be able to compress this like this, because it is already 100 mm rock wool. It is no longer 50 mm, so you won't be able to compress it like that. You need to either add on a Z spacer, or you need to do change your sequence of construction in order to be able to install properly. So what we are doing in this case, what we actually did is actually we changed the sequence of the construction. We made a little tweak to the construction sequence of the whole build roof system in order to suit to the unconventional way of laying the rock wool. So this is how it looks like, and this is what we did. So as you can see from the conventional just now, we put on the batten first, only then we put on the foil. But in our case, you can see that we are actually putting the foil after we put on the foil before we put on the battens. You can see that we put on the foil first, the Temaku bubble foil, only then we put on our battens. After we put on our battens, then only we put on our rock wool. So you can see that there's a slight difference in the sequence of installation as compared to the conventional way of the roof constructions, single skin roof constructions. Okay, so just to share with you some of the photos, as you can see here, this is how it looks like. You can see these are the foil, these are the battens. So normally when you do it conventionally, you won't be able to see these battens anymore because it is going to be under this foil. You put on the battens first, only you put on the foil, so you won't be able to see this foil anymore. And then another thing to note is also that this foil, normally when you lay the foil conventionally, you lay the foil in this direction, which is perpendicular to the direction of your battens. But in this case, you are laying your foil across the truss or in the parallel direction as the batten because of the change of the sequence of constructions. So that is why you will see all these blue colored battens on top of the foil over here. So this is the completed photos, the completed photos of the annex building itself. And you may have noticed that there are a few notch over here, as you can see here. This notch is actually a design innovation by the design architects in order to conceal the downpipes, because this roof, as I mentioned just now, is actually there's an overhang from the roof buildings. So when you have an overhang outside of the roofs, you will tend to have downpipes. You need to have downpipes to collect the water from the gutters. So when you have overhangs, the major issue with that is that you are going to have exposed downpipes. So what the architect is doing is that actually we do a T-joint over here. A T-joint, you can see the gutter, the gutter, actually there is an intersection coming in to the inside over here. So this is where we put on our downpipes inside at the same level as the building line. Okay, so that is on the annex building. Next, I will move on to the main buildings. So first, we'll go through the build-up of the entire system that we are proposing for the main buildings. So the roof structure itself, as you can see just now, the overview of the Sarawak Museum, you can see that the roof structure, there are a lot of curvy arches, big arches, small arches. So it is very obvious that in this case, you won't be able to, we will have to use mount steel structures, mount steel members in circular hollow section in particular. And for the insulation, we are, instead of using 2 layers, this is only 1 layer of 50 mm thick, 40 kg per meter cube rock wool. And the insulation that we are using is Lysaght Temaku bubble foil as well, the same as the annex buildings. And for this, because the roof covering is slightly different, so we need a roof underlay. So you can see that we are also using a roof underlay of 6 mm thick fiber cement board. This fiber cement board is at this one is the fiber cement board. So normally for seam roof, we will propose at least 9 mm thick or 12 mm for a high specifications one. Why we're using 6 mm thick fiber cement board in this case is that because of the curvature of the roof. So in order to be able to curve the cement board to the required shape, we'll have to use 6 mm because we have actually performed a full scale mock-up to ensure that this 6 mm can actually form the curve that is required by the architects. And after the cement board, we'll have a 1 layer of 1.5 mm thick bituminous felt or the waterproofing membrane on top of it. Then after all these are up, then we have our roof covering of 0.7 mm thick Lysaght 360 seam 25 in Colorbond XL. So this Colorbond XL is actually aluminium. So the difference between the main building and the annex building is that the profile and the material is different. The top skin is different. So for the main building, we are actually using aluminium as the best material in order to have more flexibility for this kind of curve. So of course, the profile is also different. We are also using Lysaght 360 SIM 25 as the profile compared to Cliplet Optima for the main building, and the thickness is 0.7 mm thick. Okay, next I'll move on to the construction of the steel structures first. So this is a perspective view of the entire steel structures. As you can see here, there are 4 main flat roofs, 4 main arches, and 28 outer or small arches. So these are what we call, if you look at the plan, these are what we call the flat roofs. Or the isometric view, these are what we call the flat roofs, the flatter roof. Yeah, it is flatter compared to all these arches, but actually it is still steeper than the annex building. This roof pitch is around 11 degrees, so it is actually still quite a moderate pitch roof. So so you can see that there are 4 flat roofs over here, and the main arches is this one. These are the main arches. There are 4 at 4 directions, and we have got 28 other outer or small arches, which is at outside of the buildings over here. So the erection of the structures within the building envelope are given priority to ensure water tightness of the building, so that other thread of works can be carried out. So we have to be very vigilant and careful when we are planning the construction of all these steel structures, because we have to ensure that the erection and the installation of all the components within the building envelope are installed first. Because if we are to only once everything inside the building envelope are installed, only then the other threads of work can carry it out. We need to make sure the water tightness, everything inside this region is actually watertight first before other thread of works can actually move in and start installing, such as the ceilings, internal ceilings, etc. So therefore, because we need to do whatever that is within this envelope, these perimeters, then the main priorities are given to the erection of installation of the flat roof trusses and the internal rafters of the main arches. So these are the flat roof trusses. This is the internal rafters of the arches. So the building line is actually somewhere over here. This is the building line. So this is a building line. So whatever that is within this region, we have to do it first. So this also means that all these flat roof trusses and all these main arches will have to erect first. But the main arches, the outside part of the main arches, it can be at a later stage. But this part is of topmost priority to ensure water tightness. Okay, so now that we know that we need to install all this pitch roof, all this pitch roof and all this truss arch. But what exactly is the first thing that we need to install first? The pitch roof or the arches? Actually, what we need to install, if you look at this 3D diagram, you can see that all these trusses, all these flat roof trusses and all these arch rafters and the trusses are actually connecting to one common point, which is at the center over here, in which we call it the ring truss. So this ring truss is actually what is needs to be up first in order to provide a platform for all the trusses to connect to. This ring truss over here. So, but of course, as you can see in this perspective, this ring truss are actually suspended. So you cannot have a truss just it is impossible to have a ring truss just at there hanging in the air without any support. So that is why we need to build our temporary supports first, the temporary support first. So this is how the temporary support looks like. So this temporary support, we first need to establish a platform between the two RC beams using 4 numbers of UB533, universal beam, or in layman term we call it the I-beam. the I-beam 533, and then after we have established this platform, only then we can put on this temporary support. This support is meant to be temporary, as we can, once the ring truss is up and once all the structures is completed, we can actually remove it. So this temporary support is kind of like a towers. If you look at there, if you notice, there is a 250 mm up stem over here. It is actually served as a support to actually prevent the lateral movement of the ring truss. So after all these are out, then we can put on our ring truss. So this is how it's going to look like. This is how the ring truss is going to be established. So you can see that before we put on this ring truss, you need to have this temporary support and this platform out first. If not, there won't be any platform for this ring truss to sit on. So after we put on the ring truss, then we can start installing our trusses for the flat roofs. So you can see that for the flat roofs, there are actually 3 main trusses, with one connecting to the corners of the RC roof over here, and the other 2 connecting to the edge of the main arches over there, over that side. And after we have gotten all these 3 main truss erected and installed, then we'll have all these transverse truss, which is installed to provide lateral stability to the main truss. After we have installed the flat roofs, then we can start. Then we proceed with the installation with the main arches. So as you can see here, these main arches are actually erected on the roof or installed on the roof. So the curved rafters of the main arches are fabricated and curved in the fabrication yard. So we are actually doing the fabrication. We are actually curving all these individual components, members in our fabrication yard instead of at site, because this site is the area that is allocated for us is not very big. So it will be a problem for us to actually fabricating everything on the site. So we'll have to make sure that all these rafters are actually done properly at our fabrication yard. So that is why it requires a very extensive and comprehensive detailings and curving precision to ensure all the erected curved rafters are on the same curved planes. So as you can see that this actually all these radius are different. You can see it's getting smaller, and even for a single curve like this, that it has already got 2 different radiuses already. So that is why we need to be very careful when it comes to the detailings and the precision of how we curve the rafters. And of course, the sequence of the rafters erection has to be from the inside out. So that is, it has to start from the inwards, from the ring truss towards the outwards, the outermost gable. So that means that we'll have to install this first. This is the ring truss. We need to install this first, followed by this, followed by this, and followed by coming out along the way. Okay, so after we have installed the main arches and the flat roofs, then the next one that I would like to share with you is on the outer arches of all the small arches. These are the small arches. So you can see that the size of the outer arches and the main arches are actually they're actually quite different by quite significantly. So the components of all outer arches, such as the rafters and the tie beams, these are the curved rafters. These are the tie beams. All these things, all these individual components, loose components, are actually fabricated in the fabrication yard also, just like our the main arches. All these individual components are also fabricated in the fabrication yard. But the assembly of the components are actually done at the site on the ground. So as I mentioned just now, the main arches, we do it on the rooftop, the assembly and the erection, because it is too big. But this one, it is much smaller. So we can actually do this fabrication, everything over here, including the purlins, tie beams, rafters, purlins on the ground, at the ground level. So the setting out of the base plate position is also done on the ground by using mount steel members to fix the bases in position. So these are the mount steel members. So we are actually using this. We go and get the measurement at the rooftop, and we find we will get the exact measurement and compare it with the ARCI or the structural drawings to make sure it tallies. If it is differ, then if it is not difference by too much, then we will do it based on all this setting out on the ground. So this actually helps us, because when we do it on the ground, the process will be much smoother then, and there will be less safety concerns also. So only after we have erected and assembled everything over here, then we'll lift this entire outer arch up to the roof level and install it. Okay, so that is on the roof structures. Next, I would like to share with you on the installation of the roofing system. Okay, so just to recap, this is our roof system built out. If you look at this, this is the purlins. This is under structures. After we have put on the mousy rafters, then we put on the purlins. These are the purlins. And one thing to note that is that these purlins need to be spaced at 600 mm center to center, in contrary to the normal practice of 1.2 meters, because we are actually using cement board as our underlay. So after we have put on this, we can put on our thermocool bubble foil across in the same direction as the roof, and then we put on our Z spacer. This Z spacer is actually serve as a gap filler to accommodate this 50 mm rock wool. And after we have got this rock wool up, then we can start laying our sandboard. And this sandboard will be followed by a bituminous felt, and then the seam roof. So I will show you some of the construction photos for your ease of understanding. So the first one would be the installation of, after we put on the purlin, we need to put on the bubble foil and the Z spacer first. Okay, so this is how it looks like. So our Lysaght thermocool bubble foil are to be laid in the direction perpendicular to the purlins. So purlins is in this horizontal direction. So our foil is laying in this direction, in the perpendicular directions to the purlins. So unlike ANNEX building is parallel to the direction of the purlins, but this one is perpendicular to the direction of the purlins because we have got Z spacer over here. And of course, some drillings you need to fix some self-drilling screws need to be fastened to fix the bubble foil in position prior to the installation of Z spacer. Because before you put on this Z spacer, when you lay this rock wool all the way down to the roofs, you need to temporarily fix this thermocool bubble in position first, in order to prevent, because this is a steep roof, to prevent the foil from slipping and sagging. So you need to fix them in position first, and only after you have secured it in place, then you can put on your Z spacer. And your Z spacer is actually installed in the parallel direction to the purlins. So wherever you have your purlins, you will have your Z spacers. So you cannot skip your Z spacer in this case. So if your purlins is every 600, then you need your Z spacer at every 600 mm center to centers. Okay, after we put on the Z spacer, then we can start laying our rock wool. So this is the rock wool. So the rock wool are actually laid in between the Z spacer to fill up the gap between the Z spacer. The Z spacer of the height of the Z spacer is 50 mm thick, so it is exactly the same height as the rock wool. And this rock wool, normally rock wool comes in two forms, one in slab form, one in blanket form. Blanket form is the more commonly seen one, where it is in roll form, but this slab form is actually in piece by piece. So the dimension of this slab rock wool is 0.6 meter, 2 feet times 4 feet times 50 mm thick. So that is one of the reasons why we are actually trying to fix our purlin spacing is 600 Jun also, because we want to make sure that it fits perfectly to minimize the trimming and the cutting of the rock wool. Okay, after we have laid the rock wool, then we can start laying our fiber cement board. Okay, so this is how it looks like once the fiber cement board is installed. As I mentioned just now, the thickness that we are proposing for this fiber cement board is 6 mm thick due to the curvature of the roof. And of course, it is also best to have the fiber cement board span across as much support as possible. And so that means that the sandboard shall be laid in such a way that the longer side of the sandboard should be perpendicular to the purlins and Z spacers wherever possible. So if you look, what this means is that if you look at that, our sandboard comes in a dimension of 4 feet by 8 feet. This is 4 feet, this is 8 feet. You can see these lines here are actually the size of the sandboard, and these are the joints area. So you can see that the longer side of this sandboard, it is best to have this longer side of the sandboard in the same direction of the roof, or perpendicular to the direction of the purlins, so that it can span across multiple purlins to have maximum strength. And of course, on top of that, countersunk screws shall be used to install the sandboard, so that there won't be any protrusion of screw head, which may cause problems for installation of the top skins. So for the screws that we use to secure the sandboard, it has to be countersunk screw. So countersunk screw is actually a flat screws. Normally, the one that we use for the trusses are actually hexagon head screw, where there is a protrusion of the screw head. So in this case, we won't be able to use this, because if we are to use this, we will have problems installing our top skin later, because you will have a screw head protruding out of the top skin, which is not going to look good. So after we have laid the fiber cement board, then this is how the bituminous felt look like. So it is also length. The length method is more or less just like the foil. It is also comes in roll form. You lay it all the way down with some lapping at the side over there. So it is quite straightforward. And after all this, all the bituminous felt are laid, then we can start with the laying of our top skin, and the most important one, our Lysaght 360 SIM 25. So just to share with you, the cover width of our 360 SIM 25 is actually 531 mm wide. This is what we call the cover width. This is 521 mm. So this is a very wide profile. So this is also a concealed fixed profile. Like clip lock, it is also a clip system. So you won't see a lot of fasteners on top in the middle of the roofs. And the reason that we are actually using SIM 25 compact, why we are not, some of you may have this question in mind, why we are using SIM for the main roof and using clip lock for the annex building. Why are we not using clip lock for all of them? The reason for this is that because for this one, it is not as simple as annex building where it is just a flat roof. This annex building is a very complex. The shape of this building is very complex. There are a lot of arches, so that is why we need a profile that has very high flexibility and high formability. And this is where 360 or 360 SIM 25 comes in, because it can form a lot of different shapes. Because for Clip Optima, you can already roll this kind of profile. Straight profile means that the width of the cover width of the Clip Optima is 980. Means that you will have this cover width consistent throughout. So there's no way that you can taper it. There's no way that you can curve it also using machine. So you won't be able to do this with Clip Optima. But you can do all this with our 360 SIM. So that is why we're actually using this profile for proposing this profile for the main building, because of the complex shape. Okay, so that is on the roof system build up. Next, I would like to share a bit with you on the roof length sequence. So as you can see that the pattern of the installation sequence is that we'll install the flat roof first. This A is the first one that we install. So we'll install the first roof first, and we'll install another adjacent first roof next to it. And the third one will install the main arches over here. The reason why we're installing this in this pattern or in this mode is that we need to get the gutter installed first before we are able to install the top skin. If we are to install all the flat roof without any main arches installed, then we won't be able to install the gutter. When we are not installing our gutters, we won't be able to install the top skin. So that is a problem. So if we are to install all flat roofs, we will end up with not installing any of the roofing sheet at the end of the day. So that is why we are doing it this way: 2 flat roofs and 1 arches in the middle. One this arches is up, then we do this part followed by E, and then F followed by G, and then only then we move on to the small arches, outer arches at the outside of the building, because these are less critical, because actually they are outside of the buildings, so they won't have too much water tightness concern. Okay, so I mentioned about the gutters just now. So I think one of the key things that we need to look in detail for these particular buildings is actually the gutters, because water drainage is very important. We need to identify where the water flows to ensure that there won't be any water overflow or leakages problem at the end of the day. So this is, just to recap, this is the roof plan of the main building, the main roof. So if you look at this, actually there are a lot of gutters inside there. So I mainly categorize them in four types. So I will start off with the first type first, and the smallest type gutter first, which we call the arch gable gutter. So this arch gable gutter are located at all these red lines over here. So these are at the slope, slanted gable overhangs over here, as you can see it. So these are the arch gable gutter. These are at the protrusion or the slanted eave of the gable. So as you can see that this gutter is relatively small, and the specifications of this gutter is exactly the same as the roof. So this is exactly the same material as the roof. It is also using aluminium. It's formed using aluminium, and you can see that it is actually relatively smaller. And it is also at a slope, so we wouldn't have to worry too much on the joint area over here. And you can see that there are a lot of small, we need to cut it into a lot of small, shorter pieces in order to be able to segment it, because this is a very curvy roof. So we'll have to divide these gutters into a lot of segments. As for the gutter supports, you can see that we actually extend a piece of equal angle over here at the bottom as a gutter support to support the gutter outside of the rafters. Okay, so these are on the gable gutters. The next gutters would be the valley gutter between the arches. You can see that these are the arches. So between these two arches, the water from these two arches will fall into these valley gutters, or what I would term as G2 in this presentation. So all these yellow lines over here are actually the G2, or the valley gutters between arches. So this is how the valley gutter looks like between the two arches. Okay, so this is how the details looks like. We have a gutter clips to be hooked onto the purlins at both arches at every 600 mm to center to center. After we put on these gutter clips, then we put on our gutters. And for the material of this gutter, we are actually using stainless steel gutter compared instead of the aluminum gutter. We are using 1 mm thick stainless steel gutter because this is a flat. This gutter is a flat gutter. There's not much gradient. The gradient is very low. So that is why we will have to make sure the joints are well taken care of. Because when we use aluminum gutter, yeah, we can, because it is at the gable gutter, the gutter is at a gradient. We can just lap it. As long as we lap it correctly, the chance of water going in is less likely. So in this case, it is the gradient is very gentle. So we have to make sure that all these joints are properly well taken care of. So that is why we are actually using stainless steel, because all these joints can be welded, and the welded joint will be definitely much less susceptible to any compromise over time. Okay, next is G3, or what I call the valley gutter between the arch and the flat roof. Just now we talked about the valley gutter between these two curved arches. Next, this one, the G3, is the valley gutter over here, which is between the main arches and the flat roof, or the blue lines over here. Okay, so these are how the valley gutters looks like. So this valley gutter, the specifications, the materials for this gutter is also stainless steel, 1 mm thick, and the mode of construction is more or less the same as the G2 also. It is also using a gutter bracket that is hooked to the purlins first, and then we at every 600 mm center to centers, and followed by our stainless steel gutters all the way up to the top, the apex of the roofs. Okay, so last but not least, the mother of all gutters, the main gutter, G4. So this G4 is the biggest gutter of all. It is a gigantic gutter where it collects all the waters from G1, G2, and G3, and all the roofs over here. So it has to be very big to ensure that it has enough capacity to actually collect that much water without overflowing. So this is how the main gutter looks like. Okay, so you will see that because this gutter is too big, it is so big that we have to specifically design supports to actually support this gutter. So we are actually using this blue colored material. Is actually our It is actually the same component as our smart truss, our true core materials. So to do a kind of something like a truss over here as a support to support this gutter. And we also have to put on one layer of cement board, 6 mm thick cement board, as the gutter substrate to prevent any to minimize the chances of any ponding issue. So you can see that this gutter is so big that this is 1.4 this is 1.5 meter tall gutter. You can see there's even a small ladder over here, because once you get in the gutter, you will have a very hard time to climb out, because it's a very big, huge gutter. So it is so big that we'll have to divide this gutter into 3 segments, because one gutter, the raw material, when it comes in sheet form. So that sheet form is actually in the form of 2.44 and 1.22 only, 4 feet by 8 feet. So this is way exceeding that figure already. So that is why we need to divide it into multiple pieces and make sure that eventually and all this has to be properly welded to make sure that they are 100% watertight. Okay, so this is on the gutters. Okay, so now that I've explained to you on all the types of gutters and their functions, the next one that I would like to share with you would be on the detailing on the intersection of these gutters, because you can, just now I mentioned to you G1, G2, G3, G4, and eventually all these gutters are going to connect. So this is where special attention needs to be paid to also when we are doing the detailing, because we have to make sure that all these gutters actually connected properly to ensure that there won't be any problems or issues at the end of the day, because we are talking about a very, very big catchment, a huge chunk of water that is going to be collected at the end of the day. So this is how the intersection of the gutters look like. So this is the G1, the eave gutter that I mentioned just now, the gable gutter. All the water from here will fall all the way down together with all this roof sheet will fall the way down into the gutter G2, which is the gutter between the valleys, and the water inside the gutter G2 will eventually falls into the mother of all gutters, the main gutter G4 over here. And at the same time, G3 between the main arches and the flat roof will also falls into this G4. So this is how the connection looks like. And if you notice closely, you will see that even though this height is 1.48 meters, the height of this G4 is very, very huge, but the effective depth of this G4 is at this level only, because it is governed by this level of G2. This level of G2 will govern the effective depth of this G4, because once the water in this G4 exceeds the soffit of this G2, the water will tend to backflow outwards already. So when it exceeds the level of the top of G2, then it will tend to overflow already. So that is why during the construction of the steel, we will have to make sure all this level has already been taken into account already during the constructions. Okay. So next, on the construction and I would like to share with you on the manufacturing process of our 360 SIM25. As you can see that it is actually not only that it is a very complex roof, it is also a very long roof. So as you can see here from this plan, this is a roof sheet that has already been lifted up to the rooftop. You can see that this is a very long roof. This roof is in the length of around 32 meters. So 32 meters is a length that we are not able to, I don't think you will be able to find any lorry or trailer that will be able to carry such length to the site already. So definitely, even if we are able to roll this piece of roof in the factory, we won't be able to transport it to the site, because I don't think there is such trailer or mode of transportation that allows this kind of length of roof to be on the road. So what we are actually doing is that we are actually mobilizing our whole SIM25 machine to the site and roll the entire piece on site, because we do not want to do it in a lapping or 2 pieces. So that is why we are actually mobilizing our whole entire machine to the site and roll it over here at the level 2 area, or if you look at it, it is at here. So if you still remember just now, if you recall, just now, this is exactly the area where we are actually doing the fabrication of our lightweight truss for this annex building just now. So this is like a very useful place for us to do all the manufacturing over here. So we are actually roll forming all these long length sheets at the level over here. So after we have rolled out all this, only then we'll leave it up all the way to this level, to the level over here. And of course, the lifting process you need to be very careful. So I will show you some of the video on how the lifting process is done. So this is how it looks like. So when you lift your seam roof, you cannot just simply lift like that. You cannot just put a sling on the of our roof and then just lift. It's going to eventually break because it is very long length. So what you need is that you need this spreader bar. You see the triangular truss over here. This is what we call the spreader beams or spreader bar that can provide strength to the roof. So what you need is in lifting this kind of long length roof is this spreader bar. Okay, so you can see that this is a very tedious process because by lifting this piece alone, it will take you probably 15 minutes, 30 minutes just to lift it up to the tops. So it is going to be very time consuming. It is a very time consuming process to actually lift the whole thing up to the roofs. Okay, after we lift it up to the roof, then we curve, because the roof that we roll out is straight roof. It is not curved yet. So we need a special curving machine to curve the roof. So after we lift the straight roof are rolled at this area, we'll lift out to this area over here, and then we'll do the curving on the rooftop. So our curver will lift this curver. This curver is much lighter compared to our 360 seam roll forming machine. So we'll lift out this entire curving machine up to the rooftop over here and curve this thing on the roof, and then we'll mobilize it by manpower to the respective area which requires such curved roof. Okay, so at the back of the archer, just now for the front, it is actually using composite panel to finish this off. But at the back of the roof, at the rear part of the roof, we're actually proposing our Lysaght custom op as our rear cladding to finish off the gap between to cover off that hole at the rear part of the outer arches. So this is our Lysaght custom op in Capero-Melanic. Okay, so last but not least, the safety. So I would like to share with you some of our safety innovation or initiatives that we have taken in these projects. In Bluescope, safety always comes on top of everything, and there shall never be any compromise when it comes to working safely. So even though we are facing a lot of time challenges, we need to complete it in time. We need to make sure everything is done in a timely manner. So we need to ensure that everything is at its most efficient state. But when it comes to safety, we'll have to put all that below safety. Safety always needs to be on top of everything, because we cannot afford to risk any of the installers of our workers' life when it comes to the installation of especially when it comes to such complex building. So therefore, a lot of risk assessments need to be carried out prior to the kickoff of the projects to ensure that all potential safety issues and the hazards are addressed. And the key challenges that we actually face when it comes to the project execution is to establish a safe access and platforms, especially for the steep and curvy arches. So that is why we need to always stay innovative to ensure a safe, practical, and out-of-the-box solutions. So in this case, what the main challenges that we are facing when we are installing the roof is that once we have got the purlin out, yeah, we can still step on the purlin with the OS mesh. It is still not much of a challenge because this actually serves as a stepping point or a platform for us to actually access to the top of the roof. And we can hook our lifeline or the lifeline support at some of the purlins or the mount steel over here. So actually it is still not much of a concern, but the problem comes when all these underlay are up. Because all these underlay are up, you won't have a platform to actually step on already. You actually need some kind of ladder, custom-made ladder to climb up to the tallest part or the highest point of the roofs already. So that is why we have tailor-made something that we call the safety ladder, particularly for this project. So this is the safety ladder that I mentioned just now. So this is this thing are actually some of the innovation that that is tailor-made for particularly for these projects. So the vertical components of this ladder is actually using our poly pipe 20 mm with thickness of 3 mm thick. And the horizontal, the steps over here are actually using Serangan Batu timber 1 by 2 inches. So you can see that there are two rows of lifeline over here. So the lifeline on the right is actually to serve as a platform for the as an anchoring point for the rope grab to be secured on. So this rope grab, for those of you that are not familiar with this, is that the use of this rope grab is actually, it is also a part of the fall arrest system. It's just that it can, when you go up, you doesn't need to release it to go up, but when you comes down, you need to manually release it so that you will be able to come down. Later I will show you a video on how these things work. So this lifeline is actually used, is actually serve as a point for the rope grab to connect to. And this lifeline on the left side of this installer is actually for the double lanyard to be hooked to. You can see that the lanyard over here, there are 2 of them, which are actually going to be connected to the back part of the workers, to the body harness over here. So this why we are using double lanyard, because when you go up, you need to release 1 lanyard. At least when you are releasing this lanyard, at least this lanyard are still connected to the lifeline over here. So once we put on this to the upper part, then we can release this one, so that there is no window of risk during the installation process. And all these lifeline are going to be eventually secured to the ridge over here, the ridge support and the wire rope over here. So this is how the whole this is how I will share with you how these things works. So the going up, I will share with you on how does the going up process looks like. So this is how it looks like. You can see they release one of the lanyard when they are going up, and they hook it, and they have to pull this and put on again. As you can see that at the same time, this rope grab also sliding up. It doesn't require any thing to be done to it at the moment when it is going up. Okay, so when it is coming down, it is slightly different, because you will have to release this rope grab. This rope grab, when it goes up, it can just follow. But when it comes down, you will have to release it, and it is actually a safety. It is a safety function to prevent any potential unexpected fall. So as you can see that when the installer coming down, they are putting off this. When they are disengaging the lanyard, they will have to go all the way back up and release this rope grab. And of course, for all these ladders, we'll have to, apart from getting all the certifications required for the components that we use for these safety systems that we are adopting, we also need to ensure that the ladders that we build are actually capable of sustaining the fall impact of the workers. So that is why we actually do a real scale, full scale load test for the ladder itself. So this is the video of our test. So you look at this is actually our waterproofing membrane. One row of this waterproofing membrane is around 40 kg. So you can see that we are actually using these 4, there are actually 4 of them. So it will total up to around 160 kilo. So it is more or less equivalent to the weight of two workers, which is working on top of the roofs. So you can see that it actually is able to sustain the weight of at least two workers, which is working on top of the roof. So we actually done simulation to ensure that the ladder does has enough capacity to cater for the weight of the workers that is working on top of it. Okay, so the next one would be the one just now I mentioned about 2 rows of lifeline that is connected to the ridge. So the first thing that we need to establish before all this is actually the ridge support. So this wire rope. So I would like to share with you on the sequence on how this is installed. If you look at this is a GI bracket followed by a threaded rod. So first, once we have got the purlin up, then we can put on our GI bracket. So this GI bracket is this one. So once we put it in at certain intervals, then we can put on our threaded rod. So this is the threaded rod. This rod need to be a threaded rod because why we are not doing this at a single entity, we just weld it. The reason is that because we will have to remove this letter, or else it's not going to look nice. If you imagine if you have all this threaded rod to be used as a permanent thing, as throughout, as a finishing, as a permanent features of the entire of the museum, then I don't think people will like it. It's not going to be aesthetically that pleasing as well. So that is why we have to use a threaded rod to make sure that we can actually remove it at the end of the day. So after we put on the threaded rod, then we can pull through this 12 mm wire rod across it. So after we have got this established, then we can put on our roofing. Okay, so this is what it looks like after we put on the roofing and the threaded rod, and these are the 12 mm wire rod, diameter wire rod, to serve as a anchoring point for the lifeline. So after we have after the establishment of all this, then we can start establishing all these ladders and all those stuffs to start the installation of all this roofing. And after the installation of the roof is done, all these seam roof are actually after it has already been installed, then we can remove this threaded rod. This is what I mentioned just now. This actually there's a thread over here. You can just pushing just like the screw, just remove it. Okay, after we have removed it, then we can cover it with our ridge capping. So you won't have any trace of screws or puncture on top of the roof over here at the end of the day. Okay, so this is how it looks like after the installation of the ridge capping. So you won't be able to see all the threaded rods, and you'll be able to see this. So the next thing some of you may have question in mind that after I remove this threaded rod, how am I going to climb out to the top of this to remove? First thing, to remove it, and second, how do and to install the ridge capping. So this is what we are doing. So we are actually introducing these special steel ladders on top of this with a special clamp that is clamped to the ribs of the seam roof. So once we have got all the seam roof covered, then we'll start installing all this ladder with a clamp over here, which is going to be clamped to the ribs of the roofs, and then we access to the rooftop using all these ladders, custom-made ladders, to remove all these threaded rods as well as to install all the ridge capping over here. So finally, this is just to share with you again, this is the completed photos of our Sarawak Museum. So with that, I conclude my presentation. Thank you. Any question?